Good morning, Caitlin. Good morning, Caitlin.
Good morning.
I assumed you had a speaker, so. Your first year, did you have any questions?
I don't think so. Not right now.
Gotcha. How's the material going? Does it seem pretty straightforward?
I'm getting there. I've never been like great at science. So it's a lot, but I'm working on it.
So let me share screen. I'm going to jump to this guy. So this is basically the PowerPoint from 21st Century Astronomy, Chapter 3. The main thing is that we're going to be discussing sort of the scientific revolution and the Copernican revolution. And I treat those as two separate things. A lot of people do. Some people just say they all happened at once, but the scientific revolution is basically about people not listening just to authority anymore, people actually wanting to do experimentation to determine what's true and what's not. Whereas the Copernican revolution I treat slightly separately because Copernicus offered us a new model of the solar system, which in that time was more or less considered the universe. But he offered us a new model of the solar system where we're just another, a third rock from the sun. In other words, we're not quote unquote special. There's no reason to believe our particular portion of the universe has laws that are different than other portions of the universe. Stuff like that. I tell my students that if you've ever seen those T-shirts with a big spiral galaxy printed on the front, and it has a arrow pointing to a small insignificant dot in that spiral galaxy, that is the essence of the Copernican revolution. So is, for instance, the theory of evolution, where there has been millions and millions and millions of species. We are but one of those species, and many of them have gone extinct. And the ones that do exist, we're just all related to them. So in some sense, we're very, very important because we're related to all those species. But in another sense, we're just another branch on a tree, if you will, the tree of life, that is. So that's the main differences between the scientific revolution and the Copernican revolution. And the scientific revolution, though I emphasize that it was brought in by Galileo, there's actually a lot of different people doing a lot of different things, both before Galileo and after Galileo, that are more or less people trying to figure out science. So we'll go from there and see what happens. So this is a diagram of basically the Ptolemaic model. So in the Ptolemaic model, basically we believed we had the Earth at the center, and then outside of that was the moon orbiting the Earth. So you see here it says Lunae. Then outside of that is the orbit of Mercury. You can see that sort of looks like the word Mercury. And then Venus, which also looks like the word Venus. And then the sun orbiting outside of that. And then Mars. And then Jupiter, that's Jovis. So you might recognize it more that way. And then Saturn. Remember, that's the only planets we knew. And that's, in fact, why we have 7 days of the week. You can trace back the etymology of the names used, and you'll see that basically the bodies that we see are in space are actually the predecessors of our days of the week. Obviously, you can see Monday is Moon Day, Sunday is Sunday, day for the sun, and Saturn is Saturday. The other ones are a little more obscure, but you can actually get it. So Wednesday is Woden, which is another name, of course, for another god, so on and so forth. But you can go through the etymology and see that is ultimately why we have 7 days a week. So it was what we call the Ptolemaic model is what we call a geocentric model. It had the sun the Earth at the center, i.e. geo. I don't know why I keep saying sun. Anyways, the interesting thing about it is the ancient Greeks did actually consider a sun-centered model In fact, Aristarchus, we're not really sure why, but he actually proposed the sun-centered model. But the ancient Greeks looked out into the night sky and realized, hey, if we were actually orbiting the sun, going around in circles in the sun, then if I look at a distant object when I'm on, say the far right side of the sun, and then I'll look at another distant object when I'm on the far left side of the sun, I should see it move back and forth against the things that are even further away. You can demonstrate this by putting your finger in front of your nose, maybe let's try about 6 inches in front of your nose, your index finger. Close your left eye, and then your right eye will be open, and that sort of represents the Earth, let's say in June. And then if you close your right eye and open your left eye, that represents the Earth in roughly December. And what you'll see is that finger moved remarkably far across your field of vision from those two positions. Now, if you take your finger and stick, instead of it being 6 inches away from your nose, stick it out about 2 feet or as far as you can, and do the same thing, you'll see that, yeah, the finger still moved, but it didn't move very much compared to the first time. So that's actually what the ancient Greeks realized would happen if we were actually moving. So when they didn't find that motion, they decided that either the universe was really, really big, unimaginably big, and that's why they couldn't detect that motion back and forth, or we were the center. Well, they couldn't imagine a universe is big enough to be so big that they couldn't see that motion, motion against the background stars. So they opted for the more convenient choice, which was a geocentric model. So the ancient Greeks did really know what was going on. They knew very good arguments for it. They didn't understand some of the other arguments, like the argument was they didn't understand the laws of physics. So the idea was that if a bird was up in a tree looking down at a worm, and if the Earth was actually orbiting the sun, it'd be going, hundreds of miles per hour or whatever. It's actually quite a bit faster than that. But if you look down and saw a worm and lifted up off the tree and flew down to get the worm, the Earth and the tree would leave him behind. So that was a lack of understanding of the laws of physics, and that took that took Galileo to discover his law of inertia, which ultimately became Newton's first law of motion. But once we figured that out, it made a little bit more sense that the Earth could be orbiting the sun. So that's the sort of background of this Copernican model versus Ptolemaic model. So the Ptolemaic model, we were left with a Earth-centered. Oh man, I keep messing that up. With the Ptolemaic model, we were left with a Earth-centered model, and it fit the data pretty well. The only problem was these things they called wanderers, which in Greek, wanderer means is pronounced planetos. So planetos is, like I said, means wanderer, and you can see that's where the word planets came from. Over time, they watched it and they saw something odd. Obviously, the origin of the name planetos. That in that every year they saw a constellation that was shaped like what we now know as, say, Gemini, and that Gemini constellation always looked the same. But every now and then you'd get an extra quote unquote star in it, and that star wasn't a star at all. It was a planetos, or a wanderer, or a planet as we call it. And what you do is if you watch that and like drew a picture as precisely as you could of the actual constellation Gemini, you'd see that new star, if you will, that planet would actually wobble through that constellation. All the other stars in the sky look like they're glued on the inside of a celestial sphere, but these planetos would sort of wander through different constellations, and they normally moved from right to left versus the constellation, but every now and then they would start to make a loop, and then they'd move from left to right and get much, much, much brighter. And then they come to a stop and start moving right to left again. And that was something that they had to capture with these models. So the Ptolemaic model became much more complicated quite quickly. So here's a picture of how that would work. So normally you can see 1013, 1019, 1024. So in this case, we actually have a planet, a planetos moving through the constellation Cancer. So this would be Cancer. Leo would be over here. Gemini would be over here. But basically, we normally see this sun moving from right, or excuse me, the planets moving from right to left against the background stars. Now they're still rising in the east and setting in the west, which if you're looking south, you realize that's left to right. But if you compare it to the background stars, it's going right to left. So it's actually going, instead of from east to west, it's going from west to east. That's the normal motion, at least of the outer planets. The inner planets do both quite regularly because they're such smaller orbits and they're inside of ours. But as you can see, it went further left, 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 left. Then it gets to some peak point, and then the planet starts to get brighter, brighter, brighter. And then it comes to a stop again, and then starts its regular motion. This motion from right to left is called prograde. This motion right here is called retrograde. So that's what you mean when you hear a astrologer or someone say Mars is in retrograde. Okay, that just means it's going in the opposite direction. Okay. Now, in order for the ancients, for instance, the people that were descendants of the educators of Ptolemy and stuff like that, they had to adjust that model that we just saw. What you saw was just basically a series of, they look like circles to us, but they were actually envisioned as crystalline spheres. So even though it was drawn in 2 dimensions and it looked like circles, they actually meant them all to be spheres, because the teachings of Aristotle taught us that the heavens were perfect, and perfect meant that everything in space had to be the perfect shape. Therefore, the perfect shape everybody knew was the sphere, so it had to be either a sphere, or in some cases you could actually have circles, so on and so forth. Of course, the other laws of Aristotle were problematic as well. For instance, everything in heavens could not change. If it changed, it must be changing from something that was perfect to something that's imperfect, which is unacceptable. Or the other option is changing from something that's imperfect to something perfect, which meant at some point the heavens were imperfect. So that was just unacceptable as well. So we come up with this solution to account for this motion. So you still had the Earth at the center, you still had the moon orbiting outside of it, and then you had, again, on a giant crystalline sphere called a deferrent, was an epicycle, which is this guy right here, which was another sphere. And that sphere actually had the planet, in this case Mercury, orbiting around it as the center of the epicycle orbited around the deferrent. And they had a special rule, namely that the center of the Earth and the center of the Sun would form a line, and the center of these 2 epicycles would stay right on that center. So Mercury and Venus, because they were never seen to drift off far away from the Sun, they had to be tagged closer to the Sun. So what they did was they adjusted the sizes of this deferrent, this epicycle, this deferrent, this epicycle, and they locked their centers right on that line, and that would allow them to account for the Mercury staying closer to the Sun than Venus does, and that will allow Venus to also stay close to the Sun, but not as close as Mercury. And you could also, in addition to adjusting these radii, you could also adjust the rate at which, say, the planet went around the epicycle. So you could do that for the inner planets. The outer planets, you had even more freedom, because here's the Sun, but then you got to, say, Mars. And Mars, you could adjust the rate at which the center of the epicycle went around the deferrent, and the rate at which Mars went around the center of the epicycle. And the same thing with Jupiter, and the same thing with Saturn. And I think you can see, not only does that account for the wobbling motion, but it even accounts for the brightness, because the brightness would occur because obviously when let's say Mars was right here, it's closer to us, and that would explain why these sides were brighter. So that was how the Ptolemaic model accounted for the retrograde and prograde motion. The prograde motion was going on when the planets were on the far side of the epicycle, in other words, outside of the deferrent, and the retrograde motion would occur when they were on the inside. So they adjusted that, and basically this model worked pretty well, and it was accepted for about 1,500 years. But every 50 years or so, actually they constantly did it. They made these almanacs, if you will, that would tell you and leaders where the planets would be and what constellations they'd be for 20 to 50 years and stuff like that. And that was used to make governmental decisions, to have, schedule certain holidays, or if they believed in astrology as if it was a real science. So for instance, a king or an emperor wouldn't want to get married if it's an inauspicious occasion according to the stars. So they would pay astronomers, astrologers of the time, people which were like, by the way, Kepler and Galileo and Brahe and all those types of people. They would be paid specifically to make such almanacs so that governments could make good decisions. They pretty much believed in it. So when they did this, of course, every time they went back to it, things were slightly different than they had been before. So they'd adjusted a little bit. They speed up, say, this center of this epicycle. Maybe they made the epicycle a little larger, and they'd have to adjust that every year. But every time they do that, I'd say every year, every time they wrote a new almanac, they would adjust things. But they would actually hold really well for long periods of time. Like I said, 50 to 100 years wasn't unexpected. So that was the Ptolemaic model. And like I said, it worked. It explained everything. Turns out it just happened to be wrong, just completely wrong. So in comes Copernicus, and I don't really consider him to be part of the scientific revolution, even though he did certainly do something that resulted in a major change in science. And the reason I don't consider him to be a part of the scientific revolution is because his reasoning seemed really bad. Basically, he was doing just like I told you all those other people were doing, making another almanac. And he just saw how complicated things were and said, hey, we've lost our way from what Aristotle taught us. We've got epicycles and deferrents and all this stuff, equant points. The equant point was part of the Ptolemaic model. It was the point around which the planets appeared to be traveling at a uniform speed, but it was different from where the Earth was, which was supposed to be the center of everything. So that was kind of complicated. So he really was trying to find a simpler way to be closer to what Aristotle had taught us. So he's not appealing to necessarily data, evidence, the scientific method, as we've grown to call it, even though I've told you before, it's not really a quote unquote just well-defined method. But he was really just trying to get back to the ways that Aristotle taught us. Either way, he came up with a fairly correct model. His model, he said, hey, I can deal with all this stuff, all the problems that we see in a very similar way. I just put the sun at the center, Mercury orbiting outside of that, Venus orbiting outside of that, and then the Earth with the moon orbiting it, the Earth orbiting outside of Venus, and then Mars, and then Jupiter and Saturn and Uranus, and then all the background stars out there. And that was their picture of the universe. And he could even explain the idea of the retrograde motion with this, because really the retrograde motion was a matter of when the planet came closest to us. So when Mars was over here, that was when it was closest to us, and therefore that was when it was brightest. Because normally what happens, we're moving this way to the left on the computer screen, and Mars is moving this way, which is to the right on the computer screen. So from our standpoint, we're moving this way. So if we consider us not moving, that just means Mars is going faster and faster this way. And as long as we're nearly on the opposite sides of the sun, that's going to continue to be the motion. But as Mars gets closer and closer, say over to here, what we see happen is there's a point at which our speed this way is exactly the opposite of Mars's speed this way, and they come to a stop. And when they come to a stop, that's when we start to go into retrograde motion. And then the retrograde occurs, the peak brightest part is when Mars would get right about here, which is just outside of it. And then there's a point at which the opposite motions stop canceling out and Mars starts going the other way. So that's kind of complicated, and your book does makes an attempt to try to explain it as well. By the way, when he did do that, he was able to come up with very neat values of the number of astronomical units each of the planets were away from the sun, and it made perfect sense because the ones that were closest had the shortest orbital periods. In other words, took the least amount of time to complete a circle. Well, ultimately, it will be an ellipse, but he called it a circle. And then the ones with the longest distance from the sun, average distance from the sun, turned out to have the longest periods. So, 9 would be on the order of hundreds of years, and so on and so forth. So his simpler prograde versus retrograde motion model can be examined here. I like to think of it this way. I sort of think of it as if you're driving a UPS truck. I don't know if you've seen UPS trucks, but UPS trucks have a seat that sort of turns 90 degrees either way. It's like up on a pedestal, sort of like a bass boat seat. And you're sitting behind the driver's side steering wheel. Obviously, there's only one steering wheel, but you're sitting behind the steering wheel, and you flip this little lever, and it allows you to turn the seat to face the left side of the door. In other words, straight out the left side, perpendicular to the way you're going. You switch it back, you can face the actual straight ahead, which you're supposed to be driving at, and you switch it, flip the lever again, and you can turn it to the right so that you can face the passenger side door. So if you imagine driving down the street, let's say in the outside lane, because you're driving kind of slowly, because you're on the clock, right? So you're on the clock, you're driving kind of slowly, you're driving say 55 and a 55, but you are dangerously, don't try this at home, you are wearing your seatbelt, but you're dangerously driving with the seat turned towards the left-hand side so that you're seeing the fast lane cars. Now, from your perspective, if a car is going, let's say 65, then what you see is a car straight ahead of you, or actually off to your left, coming up at 15 miles per hour, because 65 or excuse me, at 10 miles per hour, because 65 minus 55 is 10. So you see this car going to the right, going to the right, going to the right. That's all well and good. That's exactly what you expect. That car is clearly going faster than you. That's like prograde motion for the planets, even though the direction is opposite. So ignore that. We're just going with a little model here. But what happens when all of a sudden the both us and the other cars start to take a right turn? Even though we're in the slow lane, which is the right lane, we're actually now on the inside lane of the circle. So by necessity, we don't have to go as far to get around the circle. So all of a sudden, that car that was moving left to right and at 10 miles per hour starts to slow down, slow down, slow down, until all of a sudden we've caught up with them. And notice they're right next to us at that point, and we start to pass them. And then the circle that we're driving around all of a sudden ends, and the car starts to speed up again, going from left to right instead of right to left. That is the essence of how this diagram is supposed to work as well. So basically what you're seeing is that when Mars is over here on this side of us, it's actually closer to us and going faster than us in some sense. Okay.
What's
All
so
right. So
interesting to me is sorry to interrupt
go
you.
ahead. No problem.
Is like the fact that all at the time all our evidence was, as you've been talking about, all based on our perspective. So in a sense their model was correct because it pretty accurately represented what we saw, and that's all we really knew in a way.
Exactly. Yeah, that's sort of the essence of it. When you're actually looking at evidence, that's all the evidence you have, and the fact that it fit made it true. I mean, and that's sort of the nature of true versus false in the experimental world or in the scientific world. Something can be true and later be false, and no one lied. Whereas the political world, we don't treat it like that. But in this scientific world, what is today's truth could be tomorrow's falsehood. And sometimes that means we originally got the data wrong, or it could mean we got the right data, but the model that we were envisioning it with respect to was off. So yeah, it is pretty neat, isn't it? So yeah, so with this in mind, he was able to create his own model, which, like I said, was instead of a geocentric, was a heliocentric model. So let me get this straight again, because I keep messing these words up, which is probably the worst thing a teacher can do. So basically, from ancient Greece forward, up until Copernicus, we stuck to the geocentric model, which was a Earth-centered model. And then Copernicus offers a heliocentric model, which is a sun-centered model, but he did so not necessarily for scientific reasons, but more for appealing to authority, namely Aristotle. Now, this model was not a big deal. It didn't hit, the church didn't get upset about this or anything like that. They just saw it as another way to calculate the almanacs, and maybe it even would save them money because, they were the ones that were in charge of government at the time, or at least some of the major governments at the time. And it was just another way. And he didn't make a big deal about it. He just said, here's my model. He did make a big deal. He was a scientist, of course, but he just didn't, tout it out as, oh, you're wrong, blah, blah, blah. So, things get a little more complicated from there on out, though. Let me see if I can Every now and then it just stops forwarding this. So the categories of planets, this is just some vocabulary. This is sort of cuts up my theme and the way I'm discussing things, but the planets closer to the sun than Earth are called inferior planets, and the planets outside are called superior. You'll see there's words like quadrature, conjunction, opposition. These are all words you're supposed to know. This diagram sort of tells you everything. So you got eastern quadrature, western quadrature. Notice when the moon is, it's in some sense in quadrature, we would have a first quarter or a third quarter, but notice we have nothing like that when we're talking about Mars being in quadrature. So just keep that in mind. It's kind of a neat thing, but you can see the bright half of the moon, or excuse me, the bright half of Mars in this case, when it's at quadrature, is in fact a gibbous phase. And the same thing down here, that's also a gibbous phase. Whereas when we had the sun here and the moon here and the moon here, we actually had a half moon, what we called first and third quarter. Superior conjunction, inferior junction, greatest elongation. The greatest elongation, we actually normally do a lab. It's a little complicated to do for you guys online. That's why I haven't rendered an online lab, but there's a pretty neat little lab you can do, and that allows you to determine the size of the orbit of Mercury. And that's based on that greatest eastern elongation and greatest western elongation. You can see that that line is actually tangent to the orbit at that point. And if you just draw that line using something like the Sky or some other software that would allow you to measure the angle between the sun and Mercury, then you would actually slowly develop a empty hole with lines that are tangent to it, and that would actually give you basically the orbit, and then you could measure the size of this orbit compared to that orbit and get a fairly accurate estimation of the size of Mercury's orbit. You can do the same thing with Venus, but anyways, that's kind of a neat little thing. So let's get back to talking about these models. So we had Kepler had introduced his heliocentric model. Another guy comes on the scene. This guy's quite interesting. I think his name, technically I read once, it's supposed to be read as Tycho, like Tygo, but he's a Dane, same place that Neil Bohr and his son were from. I think Metallica or somebody's from there, from Denmark as well. I can't remember, some rock group.
Yeah, Lars Ulrich, the drummer of Metallica.
Is it cool? Thank you.
Mhm.
I knew somebody from Metallica was, but I'm not that proficient with music, so I sometimes step in it, but that's okay. So yeah, he's a Dane. But anyways, Tycho Brahe was this really brash guy. He sort of was he was noble for starters, so that sort of helped him. He was really brilliant, so that helped him get a little bit more confidence. And he even got in a fight in college over who was a better mathematician. Basically got in a duel and had his nose cut off. And he actually had a prosthetic nose made of gold and silver that he stuck to his face with wax. So he's this sort of interesting character. He's a big guy. It's kind of funny because he's going to run into, and I said Kepler earlier, I meant Copernicus. He's going to run into Kepler a little bit later, and I sort of envision Kepler as like if anybody pays attention to modern politics, you can sort of picture Kepler like Mike Pence, really straight lace, conservative type of guy. And then Russell Brand would be like Tycho Brahe, and Russell Brand's like the guy from Get Him to the Greek, or he wrote a biography called My Bookie Wookie. But anyways, he's acts as a head-banging drug addict and stuff like that. So that's sort of the two personalities that we're dealing with here. But Brahe was actually quite smart. He convinced very wealthy people to give him tons of money. So they gave him like an island, and he was allowed to collect all the rents from the island. And the rents that he got, he used to build his observatory. And he had this really big observatory, and this was preceding the telescope, so it's kind of cool. But he was able to make really, really good observations. I think observations that were comparable to what a first or second year grad student could make with all our modern technology. But he was able to make it basically with just a giant protractor mounted on a wall. And he got the best data that had ever been gotten. Kepler, on the other hand, had a pretty bad life. He had a series of sicknesses. He had nearsightedness and all this stuff, everything that made it virtually impossible for him to be an astronomer. He had, plus he had a mother that kept being accused of being a witch. So every now and then he'd have to, stop his schooling or stop his job or whatever, and have to go fight and keep her from getting burnt at the stake or something. So it's kind of funny, but they both had their own models. So this model here to the left is the weirdest thing ever, and that's Brahe's model. Brahe's model says we have the Earth at the center, and we have the moon orbiting it. And then check this out. The sun orbits the Earth just like in the Ptolemaic model, but like the Copernican model, it has the other planets orbiting the sun as the sun orbits the Earth. So it's really a really jacked up model. So he's trying to work this out, trying to get this model to fit the data or get his data to, see if it fits his model anyways. And in the meantime, this guy named Kepler writes him a letter. Here's Kepler. And Kepler basically one day, he's a horrible teacher, not unlike me, get in the middle of my lecture and start talking about, Russell Brand and Mike Pence. That was sort of this guy. One day he's teaching like probably some kids from ages of 5 to 12 or something like that, teaching them mathematics. And he's talking about the perfect solids, and realized the number of perfect solids is just the right number to be the number of things that would separate each of the planets from one another. So he goes off on a tangent and starts to derive a model of the universe where the celestial spheres, the crystalline spheres that contain the planets, were separated by perfect solids. And he writes this up, starts working out this model, sends it to everybody he knows. One of the people he knows is Tycho Brahe. He sends it to him, and Brahe's like, man, this guy's a really good mathematician. So he asks him to come work for him. Well, Kepler comes and decides to go work for Brahe, and he gets there. And like I said, remember this guy, Kepler is like Mike Pence, really straight-laced, conservative, basically applies all the laws of the Bible very, very astutely. And it's not that Brahe's not religious person. It's more that he's just a party animal and enjoys having fun. So he gets there and he finds Brahe is just a beast, loves to party all day and all night. Give you some idea, he had a pet human, what some TV stations nowadays refer to as little people. He literally had a pet human, right? He had a pet monkey. He one time got it was either a moose or a deer or buck or something, got him really drunk, and the poor deer fell down the steps and broke its neck. Just a horrible guy in many ways. But at the same time, Kepler realized that this dude was brilliant as far as his data goes. And as it happens, basically, Kepler gets there, and Brahe's sort of stingy with the data because he realizes quickly that Kepler could sort of steal his thunder, i.e. we now remember Kepler, and very few people have heard of Brahe. So he gives them data in little trickles. Well, all of a sudden, they were partying one day, and I don't know if you know this, but nobility, they don't poop or pee. So that was the thing that Brahe was trying to keep established. So during this long party, he refused to let the commoners that was at his party see him excuse himself to use the restroom. So he just sat there all day and all night, drinking and eating and eating and drinking and drinking and eating until his bladder burst and he died of a horrible case of sepsis. It was really, really brutally horrible. But anyways, that's how he died. Brahe ultimately, his family got involved. They tried to keep Kepler from getting the data because, again, they were afraid that he would be the shining light and everybody would forget Brahe. The courts ruled that Kepler could get the data. Kepler took the data, first tried his model. His model failed, and like a good scientist, he kicked it to the curb. When it didn't fit the data, he threw it away. He tried the Copernican model. It fit the data about as good as the Ptolemaic model did, except a small deviation in one of the planets. And if I remember correctly, it was Mars. It was either Mars or Mercury. But in a small deviation, it missed a little bit, and it was like on the order of 7 arc minutes off. And much to Brahe's credit, Kepler said that he trusted Brahe's data so much that he ended up throwing out the the Copernican model and going with an entirely new model that was able to account for that small difference in measurement. And ultimately what he came up with was that it was a Copernican model, namely it was heliocentric, but it couldn't have circular orbits. So it was a monumental step that he took. And the mathematics behind him figuring this out was really brilliant, because literally he just had data like how high was the planet on such and such a day, which direction was it, 232 degrees east or what, right? Or north of east or something like that. So some really difficult data to deal with, but he analyzed it wonderfully. He came up with his laws of motion. The first law is that the planets orbit the sun in elliptical orbits, not circles. Okay, that would be a real problem for Aristotle and Copernicus, because obviously the ellipse is what we've sort of considered like a bastardized version of the circle, and obviously would not be perfect and heavenly. But a ellipse can be imagined just like you do a circle. If you drove a nail in a sheet of plywood and tied a string to it and tied a pencil to the opposite end and held the pencil perfectly vertically and the string perfectly tight, you could trace out a circle. That works great for a circle, but if you do an ellipse, you have to put two nails some distance apart, and you have to connect them with a string that's longer than the distance between them. And then you stick the pencil in there until it's taut, trace it around, and it will trace out a ellipse. And notice he said an ellipse, not an oval. Ellipse is a mathematical thing that has a very specific equation. That's really brilliant, especially when you see that ultimately the orbits are so close to circular that if I put both of them next to each other, without you doing some measurements, you wouldn't be able to tell which one was a circle and which one was the ellipse, because the ellipses that they are so close to being circles, it's almost impossible to see. So these points are called the focal points, one of which would be where the sun was. Of course, like I said, our orbits are quite circular, so these focal points, these two nails, would be very, very close to each other, making it hard to discern. There's nothing special at the other one, by the way. And this right here is called the minor axis, the vertical one here, because that's a shorter, and this is called the major axis. And if you take half of it, it's called the semi-minor. If you take half of this, it's called the semi-major. So those are some terms we use on occasion. As you can see here, that's the semi-major and semi-minor axes. The semi-major axis, check this out. The distance from here to here is the distance the distance from the sun to here is the farthest distance the planet gets from the sun, and the distance from here to here is the shortest distance the planet is from the sun. If you add those two and divide by 2, you get an average distance between the Earth and between the planet and the sun. But notice adding those two is just this plus this. So I think y'all can see this total distance, which is the sum of the two, would be the major axis. Normally I'd do a long pause for people in the audience, but anyways, that's the major axis. Now, if you take the major axis and divide it by 2, you do get the average distance between the sun and the planet, but you also get the semi-major axis. So that's why we use the semi-major axis as the measurement for how far planets are. So that was his first law. The planets orbit in elliptical orbits with the sun at one focus. Here's some various eccentricities. I don't make you do the mathematics of figuring out eccentricity and stuff like that, but the main thing is, as the eccentricity gets closer and closer to 0, the orbit gets closer and closer to a circle. As it gets closer and closer to 1, it gets more elongated, and in fact, at 1, it actually becomes a straight line. So the planets generally have very, very, very small eccentricities. In other words, the eccentricities are closer to 0. That's why they're so circular as opposed to elliptical, and that's why it was hard to tell the difference.
Question.
Yes, go for it.
So you said an ellipse that has an eccentricity of 1 is a line, right?
Mm-hmm. Well,
is that like of an infinite length?
Is that what now?
Is the line of like an infinite length?
Oh, yeah. So basically what happens when you have an eccentricity of 1, if you look at the equations that make up an ellipse, it sort of turns out to be an infinity. But if you use a software package that allows you to change the eccentricity to 1, it will become an infinitely long line.
Cool.
So it's more about mathematically, it can't really become a line. All you can say is that the eccentricity can only be as large as almost 0.999 to infinity.
Mm-hmm. Gotcha.
Yeah. Good question. And I wish I'd actually played with elliptical orbits recently, so I could better answer that question. But if I remember correctly, there was like an infinity that came in, but I can't remember if it was an infinity that came in or a 0 that came in. And that would be the difference of whether an actual line came out or if it was just computer software simulation making the line. So that's me being not as up to date on on my math of conic sections. So the second law was that the planets sweep out equal areas in equal time. Remember, Aristotle said that the motions in the heavens are immutable. They don't change. Well, that would mean things don't speed up and slow down. But in this case, he found that they did. So if you say T1 to T2 is equal to T5 to T6 is equal to T3 to T4, let's say they're all equal 30 days. What you see is that when the planet is close to the sun, 30 days go by and the planet moves a huge distance. But when it's far away, it only moves a small distance. So if the areas A, B, and C are equal, then T5 minus, or T6 minus T5 has to equal T4 minus T3 and has to equal T3 minus T2. In other words, if these areas are equal, the time that the planet traveled making out those areas are equal. That's what Kepler's second law is the planets sweep out equal areas in equal times. So what I mean by area is literally just imagine this string, a string from the center of the Earth to the center of the planet. And when you start your timer, that string makes a bold line. And then when you stop your timer, that string makes another bold line, but it shades everything in between the bold lines. Now you literally divide the number of square centimeters into here, and that tells you how many square centimeters there are in this, let's say, pizza slice. You know, it's a jacked up pizza, but it's a pizza slice, right? Well, if this time period was 30 days and so was this one, then this pizza slice has just as much cheese as that pizza slice. Now, it doesn't make that good of sense until you realize, wait a second, this pizza is, you know, got a huge chunk of crust. In other words, it's a large angle, but it's so short. Yeah, maybe this long slice of pizza with its small angle can give you the same amount of cheese. So that's sort of the ideas that we use when we think about Kepler's second law. But what it does is it tells us that the planets speed up when they're nearest to the sun, and they slow down when they're farthest away. That turns out later, once Newton develops our laws of physics, Newton discovers that it's basically something called conservation of momentum. And in fact, he also does a more general proof that the planets can only orbit in conic sections, and there's only two laws of gravity that would actually allow a perfect closed orbit that repeats itself, and it's 1/r² law, which is what gravity is, and F equals kx, which is what a spring does. So Newton takes this and runs with it. Basically, he's able to prove all these principles just from his law of gravity and our laws of physics without having to have the data at all. So it's really pretty impressive. So that's the second law. Sweeps out equal areas in equal times. And it also allows us to figure something out. Notice the closer the planet is, the faster it goes. The farther the planet is, the slower it goes. This is not what Kepler was talking about when he does his third law, but it does give you the same results. So you can immediately think, okay, Mercury, which orbits closest to the sun, must be going fastest, and therefore at least faster than Earth, which orbits farther from the sun. So even though that's not what the second law is talking about, it is completely consistent with that model. So use it to help you remember whether the planets are faster in the outer lanes or the inner lanes. So that's the law of equal areas. The third law is a mathematical one, and it basically says the square of the period is equal to the cube of the semi-major axis. So I'm going to share my screen a second, or excuse me, I'm going to share my camera for a second. Let's say stop share here. And I'm going to draw something that hopefully helps you understand this. Okay, so let's do document cam. So when you first start off with science, you look for variables that are important. So in the case of planets here, we talk about the period, the time required for the planet to go from one point on the orbit completely around the sun to that same point. That's the period, P. And the semi-major axis, A, is another one. And we measure the period in years and the semi-major axis in astronomical units for reasons that you'll see in a second. But when you're trying to see how they're related, one of the first things you might do is you make a graph of, let's say, period versus semi-major axis. Okay? And if it makes a straight line, so the dots go like this, if it makes a straight line, then you say, oh, well, P is directly proportional to A, so you can say P is equal to some constant times A. and then you just used a data for P and a data for A, and that allows you to determine C, and that should be the same for all of them. Well, when Kepler did this, he didn't get a straight line. He got actually something like this. So he said, all right, well, let's try another graph. I'm going to use a different color. This green didn't turn out so good. So let's try another graph. He says P squared and A. And this time, he still didn't get a straight line. Something like that, maybe. And I'm making up these shapes, basically. Then he tried another graph. He might have tried P cubed versus A. And still didn't get a straight line, right? So he tries P squared and A squared, or well, A squared would be the same as P and A, so he didn't try that. But he tries P squared and A cubed. And lo and behold, boom, 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 he got the straight line. So what that means is he was able to find out that P squared, the square of the period, is proportional to the cube of the semi-major axis. Now, if you have a hard time remembering this, just remember there's a place in New York City where we celebrate New Year. Does anybody know where the place in New York City that celebrates New Year is? Dick Clark used to be out there. Various actors and actresses go out there on New Year's Eve. We watch it on TV. It's a specific part in New York City.
Are you talking about Times Square?
Yes, Times Square. So check this out. The square, which is measured in years, that's a time, right? So that one's squared. So that's how you remember that. P squared is equal to A cubed. Now, here's the neat thing. Because we use units of years and astronomical units, does anybody remember what the period in years for the Earth is? In other words, how many years does it take for Earth to go from one place in its orbit around the sun to that exact same place?
1?
1, exactly. Yeah, these are easy questions, believe it or not. It's just they sound kind of weird because the way I word them.
Yeah, they're kind of tricky.
Yeah. Now, what about this? Does anybody remember what the semi-major axis for Earth is in astronomical units?
I think it's 1.
It's 1 again, yes. That's why it's so brilliant to use these units, because we have, because of this relationship that we saw a straight line, remember I can say P is equal to some constant times A. So 1 is equal to some constant times 1 is what we just found. I know that 1 looks horrible, but see the 1 and the 1 here for Earth? So what does the constant have to be? Is if 1 is equal to C times 1, what must C be?
1.
Yep. So by doing that, we get the very wonderful expression that the semi-major axis in astronomical units cubed is equal to the square of the period in years. So in other words, the constant is 1. So this is true for all the planets. So if you go back in the appendix of your book and look up P in years for any planet, you can put that in here and solve for A and get the actual semi-major axis. And then you can do the reverse. You can go through and look up the A's for each of the planets and put it in here and get the P in years. And you'll see that you're pretty close, maybe within 1 digit of the last decimal place. So it's really remarkable. And for the record, the way you do this calculation, let's say we have P is 8 years. I'm using that because I happen to know it's a perfect cube. Well, I'll put a cube on there. I happen to know it's a perfect cube. So a perfect cube makes this math really, really easy. So if I say P is 8 years and I want to know A, what I have to do is this. I say, okay, well, Kepler's third law says that I have to square P. So I'm going to square P, and in calculator speak, that means I'm going to type an 8. And I'm going to show you just one button to use. Obviously, you guys know other ways, and if you know other ways, that's fine. Every calculator, a scientific calculator, will have either an X to the Y button, it'll have a Y to the X button, or it'll have a caret button, which looks like this, okay? So whichever one your calculator has, you're going to push 8, and you're going to push that button, and then you're going to push 2. Obviously, you know there's a shorter way to do that, but by doing it this way, I can show everybody, every calculator, one button new and solve it. And you may or may not have to hit equals. Some calculators immediately spit out the result. Others require you to hit equal. And when you do this, you end up getting 8 squared, which is 64. Okay. Now you can leave that right on the screen. You don't have to type that back in again. And I recommend you don't, because it's really easy to make a typo. But now what you know is 64 is equal to p squared. And 64 is also equal to a cubed. And I want a. So the opposite operation of cubing a is taking the, anybody know? What's the opposite of cubing something?
The cube root.
Taking the cube root. And here's another thing that you're going to have to learn, but the cube root is the same thing as raising it to the 1/3 power. So by using that one little button again, I'm going to take the number 64 that was already on the screen, and I'm going to hit our one button, which is either x to the y, y to the x, or the caret button, whichever one we have. And now I'm going to hit 0.33333. You can even use parentheses in 1/3 if you want, but the more of these threes you type in, the more accurate it'll be. And lo and behold, I happen to know that this is 2 to the 3 times 3 times 3 would be 2 to the 6, and then of course the cube root of that would be 2 to the 2, so that's 4. So I know that the semi-major axis is 4 astronomical units, but watch out on my test and my practice test. I'll have A might be 4 years. I'll have B is the answer if you do the opposite order, like you cube it first and then take the square root. And then C would be like 4 astronomical units. So you got to make sure you choose the right one, right? So that's the one thing to watch out on those practice tests is make sure you not only check the number, but check the unit as well. So that's mathematically with a calculator, how you blindly take a period and turn it into a semi-major axis. Let me show you how you do the same thing now, but if I gave you, for instance, that the semi-major axis was 4 years, or excuse me, that the semi-major axis was 4 astronomical units, so A equals 4 AU, and I ask you, what is the period in years, then I'm going to show you how to do that. Now, be advised, I can hide things like semi-major axis. I can tell you the average distance between the sun and the planet is 4 astronomical units, right? That's a way of me making sure you know what the semi-major axis means. So pay attention to me changing up the wording. So what we're going to do is we're going to realize Kepler's third law says a cubed is equal to p squared. So I'm going to have to, since I have a, I'm going to have to cube it first. So I type in 4. Again, whichever button your calculator has, x to the y, y to the x, or the caret key. And now I'm going to turn that into a 3rd power. So I'm raising it to the 3rd power. 4 to the 3rd. Again, your calculator may or may not require you to hit equals. But either way, out pops 64. And then we're going to keep that in the calculator. And we know that 64 is equal to a cubed. But it's also equal to p squared, and I want p. The opposite of squaring p is?
Square root.
Yeah, take the square root. Again, you could use the square root button, but I'm just using this one button that so I don't have to show you multiple buttons. So I'm going to hit x to the y, and remember the square root is the same thing as raising it to the 1/2 power, which is a much easier decimal to put in. You just put 0.5. Again, you may or may not have to hit equals, just like I put here, I should have put here. You may or may not have to hit equals, but when you do, you will get 8. So we'd say, oh, the period is 8 years. So that's how you do those types of problems. So that's Kepler's third law, and this is one of the only 2 equations I require you guys to do in astronomy. So it's not that hard, and even then, it's maybe 5 to 8 points on a given test. But generally speaking, I get a huge success rate. Students don't miss this question too much because I show them, in gory details like this exactly how to do it. If you're more mathematically savvy, you're probably not going to use those buttons as much, and it's okay. Whatever you choose to do is fine, but that's how you have to do it. And that's Kepler's third law. Let me go ahead and go back to the slides now. So I'm going to kill this and go back to the webcam, and then I'm going to kill the webcam and go back to sharing my screen. And yes, I was much further along than that. So let's go back to where we were. There we go. So we were on this slide. So that's how you use p squared equals a cubed. I've explained sort of the science of how he figured it out. That's a very typical thing in science is you find two parameters that are important. The first thing you want to do is see how they're related, ideally keeping all the other variables constant. And the easiest way is do various powers and graph them. And once you get a straight line, you've got a wonderful expression. This is the actual graph, what it looked like. Notice he put a cubed on the vertical axis. I put p squared on the vertical axis. Doesn't really matter. They both give you the same results, but it turns out Kepler's model was in fact forward-looking. In other words, he only knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn, but when we found Uranus, Neptune, Pluto, Eris, Ceres, all of them still obeyed the laws. So it really is a law of physics, if you will. It turns out to be that this is a principle that holds for all objects orbiting any other object. So Galileo comes along. Galileo is sort of like Brahe, except he's not a party animal. He's just really greedy and wants to make a ton of money, which is fine. But he's basically, his goal is to learn as much stuff as he wants to learn and then make a profit off of it as much as he can. He died a fairly wealthy man. But he was very, very brash. He knew how good he was, and he certainly made sure everybody else knew how brilliant and good he was. So he had read about Hans Lippershey, who had created a spyglass, basically grind down two lenses and put them in a tube, and had discovered basically what we now call a telescope. Only that guy didn't turn it towards the heavens. He turned it towards, other people, distant boats and stuff like that. Galileo read about it, made a better one, and then him and possibly another scientist who was at the Roanoke Island colony were making observations with it at about the same time, but that guy was out in Roanoke, basically modern day Mania, North Carolina, and didn't get the data in time, so he's not given credit. But anyways, Galileo gets credit for the first one turning it to the heavens. And one of the coolest things he saw put that, bird looking for a worm thing to rest. Specifically, everybody agreed in all their models that Jupiter was in fact moving. So here's a vision of Jupiter one day, and it had two little dots next to it. And then another day it had two dots on one side and a third dot on the other. And another day it had all three on one side. And then later on, we even get 4 dots total. 1, 2, 3, 4. So he's not a dumb guy. He writes this up and he names them the Medicean moons. Y'all probably have a little bit more historical knowledge than me because I'm not that strong in history, even though I love to be and try to read a lot. But the Medici family was a very wealthy, powerful family at the time. And if you want to shake down someone for some money, first thing you do is name something after that family. So he named them the Medicean moons. We now call them the Galilean moons, and very few people know them as Medicean moons. And they were sort of a big deal because it refuted the idea that like I said, a bird would be left behind if it dropped out of a tree to get a worm. So yeah, we didn't necessarily know why that bird wouldn't be left behind, but here's evidence that it certainly wouldn't, because these little things, which are clearly not attached to Jupiter, are in fact following it around. So that was one of the things he noticed. Another thing he noticed was, in fact, that Venus had phases. And if you look at the Ptolemaic model of the universe, with those little cycles, epicycles and deferrents, it's impossible to have anything other than a new Venus or a gibbous Venus. And because he saw all the phases of Venus, that put the nail in the coffin of the Ptolemaic model. Now, here's the weird part. Galileo did know of Brahe's model, and Brahe's model, as weird as it was, does actually allow for all the phases of Venus. So he sort of was just saying, well, this model's ugly. I'm not going to pay any attention to that. And I'm not even going to mention it. And I'm going to pretend like it doesn't exist. So in that sense, he's not being that very honest of a scientist, but he is also very much jockeying for a position because he just feels aesthetically that would be insane for our universe to be made up that way. Again, our universe in this time just means the solar system and the stars. So ultimately, he is the one that puts the final nail in the coffin for the Ptolemaic model. He gets in a little trouble. Some textbooks have a better explanation of it than others, but at the end of the day, it was more on a technicality. Specifically, he asked initially for permission to write his book. He spoke with a personal friend of his, a cardinal, and that cardinal later became the actual pope. And he had asked that cardinal for permission. The guy was like, yeah, this would be great. It'd be a great addition. You know, people could make better models and you know, cheaper calculations, that sort of stuff. By all means, write it. Well, the problem is he wrote it. And in that intervening period, that cardinal actually became the pope. And when he wrote it, he basically did it as a discourse or a discussion between three people. It was one person who's knowledgeable and curious, but doesn't really have a stake position. It's one person that basically supports the Ptolemaic model, and another person that supports the Copernican model, but with the elliptical orbits, namely the Keplerian model. The problem is he named the person which was holding the idea of the church, in other words, supporting the church's position, he named him Simplicio, which means simpleton. That's kind of a big smack in the face. They basically call him in for an inquisition, if you will. They ask him to recant. He sort of refuses. They show him the instruments that will be used to torture him. He decides that he will recant. And they said that he says as he walks out, yet it moves. There's probably no truth to that, but it is kind of a cool story. And you can actually download the actual testimonies from the Catholic Church now. If you go online, you can get them. Get the documents in any language you want. They've been translated to various languages, and you can see the actual goings on. But Galileo, probably because he was a friend of the new pope, was given in-house arrest and said that he could never teach or write on astronomy anymore. So he went into in-house arrest and decided to try to understand motion in general so he could make sense of how Jupiter doesn't leave its satellites behind. In the intervening period, I think 100 years to the day after Galileo died was the time that Newton was born. And actually, it might not have been Galileo. That might have been Copernicus. I'm pretty sure it was Galileo, though. But anyways, Isaac Newton comes on the scene. He has a troubled life. He's got a mom. Don't really know who his dad is. He left the scene really quickly. Mom's kind of questionable morals. For instance, she sort of pimps out her son to her brother-in-law or brother or something. Basically, Newton has an uncle who's a fairly decent figure in the church, and he comes out and brings Newton books from time to time. And Newton's turned out to be this really brilliant young guy, and like the guy's bringing them books on trigonometry, for instance, and mathematics, and Newton's like doing all the proofs and finding errors and giving it back and asking for more. So he tells his mother that the guy tells Newton's mother that he'd like to send Newton to Cambridge, and she said, "Well, I can't afford that. That's just too much money." He says, "No, I'm going to pay his tuition. I'm going to get him there, and I'm going to pay his tuition and his room and board and everything." She said, "Well, that's fine, but I just can't afford to lose him. I need him here on our apple farm." So she's sort of shaking him down for money. So it ends up Newton doesn't get as well treated at Cambridge as he would have because his mom shook the uncle down for some of the money, which is kind of horrible. So Newton luckily got the kick butt job of cleaning out chamber pots for the wealthy kids as he muddled through Cambridge. He didn't necessarily do badly or greatly in Cambridge, but he did become, he did pretty well, but he did become quite famous in the end when he finally tested. But in the meantime, there was this little thing called the plague, and all the kids were sent home. Basically, they didn't know what was causing the plague, but they knew that high density areas made it worse. So they sent everybody home. And just like all our students, they got quarantined. They went to Cabo, they partied. Newton went home and discovered the laws of physics, invented the calculus, just a few things. So it's kind of interesting. But Newton did come up with the laws of physics. The first one, which he sort of commemorates when he says, "If I have seen further than others, it's only because I've stood on the shoulders of giants." That's him paying homage to Galileo, more or less, because Galileo, if you notice, did in fact come up with a law of inertia, and he basically said that it's as if an object has inertia that makes it not want to speed up or slow down from its current motion unless acted upon by some force. That was Galileo's law of inertia. And inertia is not really an answer to the question. It's almost like a word we put in there to make us feel better about ignoring Aristotle. Newton comes along and says, an object in motion tends to stay in that state of motion unless acted upon by a net external force. That's Newton's first law. It's almost identical. Not only that, you can look in the notebooks of Leonardo da Vinci and you'll find that Leonardo da Vinci made the argument that, for it is clear that if an eagle pushes down on the air with a force of 50 pounds, then the air pushes back up on him with a force of 50 pounds. That is as clear a statement of Newton's third law as you'd ever seen. So in some sense, Newton did stand on the shoulders of giants. But also, it was really because he made the speech in front of the Royal Academy, and the Royal Academy at the time was being chaired by Robert Hooke, who was Newton's mortal enemy. So it was also saying, if I have seen further than others, it's only because I stood on the shoulders of giants, not hobbits like you, Mr. Hooke. So it's also kind of an insult to Hooke, because Hooke had a problem specifically. He was a very short person and did not like the fact that he was very short, well under 5 feet, probably 4'8" or something like that. But anyways, he also was a very, very brilliant scientist, contributed greatly to science in general, but he ended up acting like Newton had stole something from him, and Newton, we're about 99.99% sure that it went the other way around. Hooke tried to steal it from Newton. Same thing with the debate on the calculus. It's almost certain that Newton came up with the calculus first, and that darn it, the other guy whose name escapes me right now because I don't know why, but anyways, he probably stole the information is a little strong word, but there's an intermediary that met with Newton, and then later met with Leibniz. That's his name. Sorry. Later met with Leibniz, and then all of a sudden Leibniz publishes his calculus, and it comes out in such a form that's so perfect and well described that it's almost as if he looked like he was cheating. Whereas Newton's looks clunky and crappy because Newton was, working it out, figuring it out as he was going. So we're pretty confident that Newton did invent the calculus, and Leibniz probably sort of took it from him.
It's funny to me. It's like, what'd you do during quarantine? I just invented like all of physics.
Yeah. I just wrote this, 700-page tome on everything that you've ever known and how awesome it is.
Not much.
Yeah, doesn't do much. So that's Isaac Newton and his laws of motion. Like I said, first law of motion: an object in motion tends to stay in that state of motion unless acted upon by a net external force. The shortest way of saying that is an object has a constant velocity unless acted upon by a net force. Net external force. Constant velocity. Velocity is like speed, but speed with a compass. It's a vector quantity, just like Vector from Despicable Me. He did evil with direction and magnitude. So that was actually a correct definition of vector. So basically, a velocity is the vector form of speed in some sense. And if something has a constant velocity, that means it goes in the same direction with the same speed at all times. And that's what things generally do, even if that speed is zero, unless something is pushed on it or some force is acting on it from the outside. That's what I mean by external force. And it has to not be counteracted by another. That's why I say net external force, because you could have, Jane pushing to the right and Jimmy pushing to the left, both of them pushing with 100 pounds. Those two forces cancel out. So the net force is zero there. So that's Newton's first law of motion. And basically it tells you that, hey, if you shoot something out of the Earth and it escapes Earth's gravity and the gravity of our solar system, once it gets out into essentially empty space, there's no forces acting on it. It's going to continue to go in that straight line forever. So that's Newton's first law. Newton's second law says, okay, well, what happens if, in fact, there is a net force? Well, that net force, F, and I usually write a sigma next to it, a capital sigma next to it, that F is equal to mass times acceleration. So a way of thinking about this is if you solve for the A, I usually use a circle here. I'll probably do another video about this, but I usually use a circle here that allows you to avoid all the algebra. But if you solve this for A, you'd see that the acceleration object gets is directly proportional to F. So that means if you double the force, you're going to double the acceleration if you keep everything else the same. If you triple the force, you're going to triple the acceleration. If you increase the force by a factor of 2.87, you're going to increase the acceleration by a factor of 2.87. But it also says the acceleration is inversely proportional to the mass when you solve for A. So that means if you double the mass, you cut the acceleration in half. If you triple the mass, you cut the acceleration down to a third. And that's all you have to do in thinking about this equation, is you need to think in terms of when I double something, does that cause an increase or a decrease in the acceleration? Or if I triple it, what does that do? Like I said, I'll show you some circles for that later on. But let's go to the third law. Oh, by the way, an acceleration is anytime the velocity changes. And often a question I like to ask my students is, how many accelerators are there in a car? And obviously, you know of the one that they call the accelerator, the gas pedal, but the brake pedal is another one, the emergency brake's another one, the clutch is another one, and then here's the big one, the steering wheel is another one. So even if you have your cruise control locked and it's perfect and it keeps everything going 60 miles per hour, if you take a turn, you are accelerating. And that's important to understand, because once you realize that, you can make the conclusion that Newton did, that the moon must be being pulled by the Earth by some force that is not like any other force. Specifically, we know the moon and the Earth aren't touching each other, yet the moon and the Earth are pulling on each other, and that's what causes the moon's path to change from a straight line to a circle.
So a
go ahead.
deceleration is simply, it's kind of like a misnomer for an acceleration that simply decreases the velocity.
Exactly. Usually we use deceleration to mean a decreasing speed, and we take no account of directions and stuff like that. But at the end of the day, unless you use a weird coordinate system, deceleration would be the negative acceleration, and that's all.
Okay.
Meaning
Gotcha.
a speed that decreased. Okay, good question. There's the A solved, or the Newton's second law solved for A. So when I have an equation like this, notice this A, you could put it over 1 and you'd see it's in the numerator. Even if you don't put it over 1, it's still in the numerator. You see F is in the numerator. Whenever you have two things separated by an equal symbol and both are in the numerator, they're what I call thumbs up, and this is the way I want you to think about Newton's second law. Thumbs up means if you double one, you double the other. If you triple one, you triple the other. If you cut one in half, you cut the other one in half. The other side of the coin is A is in the numerator, but M is in the denominator. So when they're separated by an equal symbol, one in the numerator, one in the denominator, then they're thumbs up, thumbs down. So what that means is if one goes up by a factor of 2, the other one goes down by a factor of 2. If one goes down by a factor of 4, then the other one goes up by a factor of 4. So that's the way I want you to think about most of these equations, is just in terms of thumbs up, thumbs down. Here's Newton's third law. I've once saw a book called Physics for Art Majors, and its description of Newton's third law was you cannot touch without being touched. But here's the more robust form. For every force, there's an equal and opposite force. The two forces have the same size and the two forces have opposite direction, but the key point that they're not pointing out here is that they're acting on different things. So a woman pulling a rope, let's say with 100 pounds of force, and actually in modern science we use the Newton instead of the pound. The Newton's about a quarter of a pound. So if a woman pulls, say, with 100 newtons of force on a rope, then what that means is the rope is pulling back on the woman. Notice she was pulling the rope is pulling the woman. So they're acting on two different things. So you can never add those two numbers because they're not operating on the same thing. But if a woman pulls on a rope with 100 newtons of force forward, then the rope is pulling on her with 100 newtons of force backwards. So that's what Newton's third law of motion is. And it seems like it's not that important of a law because it seems like obvious, but it really, you couldn't solve many of the problems if it wasn't for knowing this one. So for instance, if you know exactly, you say you're a perfect robot and you've got all this computer machinery inside of you and you know exactly what forces you apply to everything, and you line up on a starting block for a race and you know exactly what force you're going to put on the starting block, you still can't solve the problem of what your acceleration is going to be. You can't use Newton's second law because knowing what force you apply on something doesn't tell you what force is applied to you. But if you say this runner is able to put 400 newtons of force backwards on those starting blocks, then Newton's third law says, well, the starting blocks is going to put 400 newtons of force forward on the runner. Then you say, oh, well, that's the F that I need in F equals ma. All I got to do now is put the runner's mass in it, and I can get the acceleration. So that's one of the neat aspects of Newton's third law is it allows you to solve problems like that. It also tells you that the force that the Earth applies to me, which is technically my weight, I'm going to lie because y'all can't tell on the camera, but I weigh 200 pounds. So that means the Earth is pulling down on me with a force of 200 pounds. I'm pulling up on the Earth with a force of 200 pounds. And another thing, if you've ever tried to swat a fly in the air with your hand, I know that's not nice to do to little flies, but if he bothers you enough, you're going to want to smack him. Anyways, it hardly ever kills them. Now, if you smush them against a wall, that's a different story, but smacking them in the air, it doesn't work. And the reason why is Newton's third law. You can't put any bigger a force on the fly than the fly can put on you because of Newton's third law. If you want to drill down and see exactly how that works, you say, okay, well, I'm going to swing my hand. Let's say I'm a professional baseball pitcher. I can swing my hand at a rate of 100 miles per hour. Then I'm going to hit this fly, and that fly is going to be compelled to go from zero velocity up to 100 miles per hour in the same direction that my hand is going, and it's going to do it in a small amount of time. Well, that means it's going to have an acceleration, but the problem is the fly has such a small mass, the acceleration that is going to result will require very little force. So lo and behold, that means a small force on the actual fly, so that the fly does not really get hurt. He might get, jostled a little bit if you are a professional baseball pitcher, but he's probably not going to die. So try to punch a square of toilet paper one time, you'll see it doesn't do much. So that's Newton's third law. And that finishes this chapter, which again, this was a chapter 3 type stuff, but it's leads on into chapter 4 of the 21st century astronomy, but it's pretty much consistent with the scientific revolution. Anybody have any questions? I appreciate those of you that hung out. Yes.
So